Welcome back to the second part of this lecture. Unfortunately, I cannot be with you today. I would have really enjoyed it though. I think Monday was a great experience. Anyways, I'm pre-recording this talk for you, and I am just going to go straight through it. So whenever you feel like taking a pause, do take a pause. If you want to stop at some points and think about it, or the slides are online again, so just pull up the slides on the side and click on the links if things interest you. The second part is more open. It's more of a invitation to look at all the cool things happening in neural network research. Yeah, okay, so with this, let's get started. There's a bit more theory at the beginning and then some applications. All right, so in the first part of the lecture, we spoke about general motivation and background, basic definitions for neural networks, and a little bit about optimization, and we went through the backprop algorithm. The second part of the lecture will start with double descent, or the mystery how or why deep neural networks work, followed by a quick tour de force of cool methods and applications that are ongoing at the moment. And this might be a little overwhelming, so don't feel like you have to know everything there. Take it more like as a sample of cool things that you can do if you want to stay a bit more in this field. And then this is actually wrong. Last bit is not exercises. That should have been conclusion. Exercises are, of course, for you to follow this week. All right, so let's start with double descent. One of the most interesting things if you're coming from a statistical background that came up in the last couple of years in neural networks. So let's revisit the question that we had last lecture. And that is really, why do neural networks work? So let's take a step back for a moment and think about neural networks again, putting on our statisticians' hats, rather than engineers who are just trying to get things to work. Sorry for any engineers in the crowd who think this is an oversimplification. So as a rule of thumb, usually our model should have at most as many free parameters as we have data points. If you have a linear model and you give it more, if you give it more parameters than data points, then the question is ill-posed. You have an infinite set of solutions which all equally minimize the say the least squares error that you're trying to minimize. So like as a rule of thumb, our models should have less parameters and usually much less parameters. However, if you look at current neural networks, usually they violate this, and in fact, they go the opposite direction. And it is often the case that neural networks have many times more, orders of magnitude, more parameters than we find in our data sets. This is very puzzling. Now you could argue that, say, the famous MNIST data set. So this is the handwritten digit recognition that we saw already in the first part of the lecture and that you find in every neural network tutorial. So we know that MNIST has 50,000 samples in it. A neural network trained on MNIST usually has, I don't know, like the good models, a few million parameters probably. So let's say like a few million parameters. You might say, okay, well, but every sample in MNIST is an image on a 28 by 28 grid. So like every image has is a vector in a 28 by 28 dimensional space. And of course, that would multiply the number by, let's say, it's less than 1,000, but let's say 1,000. Which would get you in the right regime. So we would have, geez, I didn't plan this. I should have planned this. 50,000, okay. this is going to be 50 million. So this would seem more right now. You can still have neural networks that are larger than this. Maybe people have trained networks that are larger. But the important thing that I wanted to say is, even if you're doing this very generous calculation of the number of data points that you have, this is not really quite fair, because neighboring pixels and images tend to be correlated. And so the images that you see, they don't fill the whole space. Actually, it's probably 50K is too conservative, and this is definitely too generous an estimate of the individual data points that you have in your data set. Okay. Anyways, take-home message: neural networks really blow up the number of parameters, and this is also what people recommend in practice. And it's quite puzzling if you're coming from statistics, why they should work at all. Why are they different from the methods we've seen so far? All right. So let's look a bit again at how classical statistics thinks about this problem. And you've seen this already in module 2. What you're familiar with is the classical bias variance trade-off. So if you make a plot, and on the x-axis you put the model complexity. So I don't think I need to go into detail again, but like if your model were a polynomial, like this would be the degree of your polynomial, just as an example. And then this is some measure of the error that your model is achieving. And the total error is composed of 2 terms. First, we have the bias, and this goes down. So that's the red curve here. This goes down as the model becomes more and more complex. So if you want to think about this from like statistical learning theory, let's say like this is the true solution. Let's call it H star. And this is your hypothesis class. And let's say this is only linear models. Now you say, okay, well, I'm also going to consider polynomials of up to second degree. And then I'm also going to consider polynomials up to, say, third degree. And you're getting closer to the true solution. So your bias is decreasing just by assuming a specific hypothesis class. You're biasing yourself away from the true solution unless you're already in there, and that bias is getting smaller as your models are getting more and more complex. It just becomes more likely that the true model that generated data, if we may assume that, is in the hypothesis class. However, at the same time, so I've drawn balls here, and there's always like a closest point. But let's say we now have a problem of finding the closest match. So here, this was the best linear model, best second degree polynomial, best third degree polynomial. It was easy to make this here, but in practice, this is not so easy. And it also depends on the training data sets that you have. So if you have a more complicated model, it's more flexible. It can model more interesting things, but it's also more difficult to find the right one. So that is the variance term. And as your model complexity increases, the variance goes up. So one way of thinking about this is if you fit the same high degree polynomial to different data sets, it's going to fit all the data sets perfectly because it has so many degrees of freedom, but every time you get a different solution. So that's like an intuitive way of thinking about this variance. So maybe the variance is something like, how difficult is it to find this point in linear space? And then it's becoming a little bit more difficult in this space, and like even more difficult in this space. I probably glossed over some sweet details about statistical learning theory, but that's the intuition behind these two curves. And now if we look at the total error that we're getting on, say, some held test data set, it's a composition of these two things. You make your model more complex, you're probably getting a better fit of the data, but it's also more likely that you're fitting noise. And at some point, there's like a sweet spot where you want to be, where your model is not too complicated and not too simple. Okay. So that's the way we classically think about this bias variance trade-off. Okay, here again, the example that I just used. And I think you've seen this before. We have samples from this function here. First, there's a linear fit, and that's underfit. And that's underfit. All right. Okay. So in the plot on the left, you see a linear fit to the data, and this is obviously a bad fit. It's underfit. In the middle, you see a fit which is quite decent, at least subjectively judging. And then on the right, you see one which definitely has too many degrees of freedom. And this is unlikely to generalize to other samples of the data. Okay, cool. So again, same plot, just different labels. We have model complexity with model error. On the training data set, your error is getting lower and lower. So at some point, your model will just have memorized the training data points and will have 0 error if possible. So you could just put a delta function on every training data point, or you like the same thing. You could have a lookup table and say, okay, this training example, this desired output, return, okay, 0 training error. If you're looking at the test error, however, you find again the same phenomenon, that there's a sweet spot. That's just same thing again, different names, different perspectives maybe. All right, here's the shocking thing. The left part of this plot is what we're used to seeing. So this is what we've been looking at all along in classical statistics. And there, everything is as expected. The training risk goes down and down as your model gets better. There's a sweet spot for the test risk, and it goes up again in this U shape. Now, if we continue beyond a certain point, and people like to call this the interpolation threshold, although I think the jury is still out there what's really happening at that point. If we go beyond a certain point, we suddenly start seeing this magic thing happening where the test error goes down again. And sometimes it even goes down further than we would have gotten if we were only in the classical regime. This is really puzzling. So this is people call this the modern interpolating regime, where really it's a bit like where our engine is supposed to run only at until a certain speed, and then at some point someone just went beyond that and started seeing that there's much more performance to be had. Not sure if that example was helpful, but I think this was very surprising when people first saw this. It has definitely been overlooked as far as I know in classical statistics. And as I said, this is very much an open research field. So here are 2 blog posts and a paper. I don't think this is the original source, like whoever discovered this first. I don't know it. But there's some starting points for you to go and dig further. Okay, and then what people claim is that modern neural networks with orders of magnitude more parameters than we have data points usually fall on this right-hand side of the curve, where you make them larger and larger, and still you don't see overfitting. Still, your performance is getting better and better. Maybe you remember the curve in the first part by Andrew Ng, where we said how much data and compute do we have, and what's the what's the performance of our model. And we saw that for deep learning, this just kept on going up. And so one idea why this might be happening is that we're in this interpolation regime, and we just keep on going down that way with the test error. Okay, but this is all very hand wavy. There's a lot of nice theory in there if you look at the original resources, but it's open research. If you want to make an impact, then I think this is quite interesting. Okay, now the cool thing is, okay, the key idea behind this is interpolation. Putting delta functions on your data points is a bad idea. If you have again our standard example, the polynomial. So if you just say, okay, at this value I'm going to output this, at this value I'm going to output this, at this x this, that's going to give you 0 training error. But of course, that's an extremely bad model of the underlying function, unless your underlying function is this weird spiky thing. Instead, if you learn to interpolate between your data points, like let's say, okay, same data points approximately. Here, I wanna give at the first one, I want to give approximately this value. Okay, and then I want some reasonably smooth interpolation between these. So I'm starting to connect this again, just with a linear interpolation. I'm not sure how much this is helping, but the idea is that you're not just putting these delta functions, you also have like some concept of smoothness. There are some really cool discussions. I hope I put the references in. I think I put the references in later, where people are discussing the problem with interpolation in high dimensional spaces. In a low dimensional space, I can just draw a line between 2 points. In a high dimensional space, this concept of interpolation is becoming much more difficult. I hope I have the references later. If not, I'm going to add them to the PDF. All right. Okay, this is a really cool example. This is from the Statistical Learning book that we've mentioned before. It's chapter 10 on neural networks again. And I really enjoyed this because it shows that this deep double descent, as we call, or as this like double shape. So we first have a U shape and then like a second descent. This double descent also happens with classical methods. So here, the authors of that book used a spline-based regression. And we have first in blue, first in orange, the training error, and this goes down. As expected, the model gets more common. You're using more and more spline functions. You're becoming more and more expressive, and training error goes down. Test error has this cool shape that we have a U shape as expected, and then we are seeing a second descent. It's not going all the way, like where at some point it goes up again, but still we have like this double descent, which is quite cool. And if we look at what's happening at individual points, I think this is a great illustration. So at 8 degrees of freedom, I think this is about the sweet spot of the classical optimal model, so to speak. And we see a reasonably good fit of this data, which is sampled from a sine function. If we're going up further, 20 degrees of data, 20 degrees of freedom, I think we have in this example 20 points. So this is a terrible fit. This is like total overfitting. And what the model is doing here, it's basically putting one spline basis function on each of the data points, incurring an extremely high test error out of the plot. But then this funny thing happens. We keep on going up. We're going to 42, and suddenly it starts coming down again. And we're actually getting something that looks again kind of like a decent fit. And at this point, I think the idea here is also that you're introducing too many spline basis functions, and by doing that, you're getting some notion of smoothness for this function that you're trying to model. Again, this is, or Again, it's probably not the case for neural networks as people hope, but at least with the spline functions at 80, it's becoming spiky again. And that's probably why the test error is going up again. But I thought this was a really cool example. If you want to, it's like 2 pages in that book. So read through it again and like develop your intuitions. I think this is really cool to see this also happening with the classical method that you've seen before in this lecture. All right, a couple of bullet points on this, possible explanations and consequences. So infinitely wide neural networks are equivalent to Gaussian processes. I'm just going to drop this here. It's based on some really cool work that David Mackay did in the 90s. So as you're making a neural network infinitely wide, there is some equivalence there that you can define between a neural network and a Gaussian process. I don't think Gaussian processes were covered in this lecture series, but feel free to put that into Google and look them up. They also basically operate on the idea that you have a non-parametric way of fitting a function after deciding for a given level of smoothness, or even determining the smoothness from your data. So like with this idea, we have like a non-parametric way with some smoothness level where that's building up some intuitions towards what we just saw with that curve fitting example. Training neural networks with stochastic gradient descent may encourage smooth solutions that interpolate between training data points. So there has been some work, and I wasn't able to find the references. I hope I can put them in the slides later, where people investigated what sort of solutions you find with stochastic gradient descent. And if I remember correctly, they tended to find that the weights are converging to the smallest norm, like say the smallest L2 norm. On average, this is like again like a kind of hand wavy statement among neural network researchers. And in this context, the solutions that you find with stochastic gradient descent tended also to find like reasonably smooth solutions. So I mean, if you have infinitely many parameters, like nothing stops you from just building this spiky weird thing that doesn't generalize at all. But there must be some, let's call it magic, happening during this SGD optimization. And if you're coming from a mathematics background, I think, as I said in the first part, this is one of the big riddles to figure out in the next couple of years. So go for it and find out why this is happening. Okay. It's an open research area. Here's another reference to a blog and a paper. Common practice in deep learning, choose a neural network that is larger than necessary and use your engineering intuitions that you developed on previous problems. And this is a bit of the point, or like the issue that we spoke about earlier. There was a famous talk 2 or 3 years ago at a big conference where someone argued that building neural networks is like the modern alchemy. You're just trying out buttons and mixing chemicals until eventually something fun happens or something happens that works. So this is one of the intuitions. If your model is not doing well yet, maybe you can push it further into this interpolation regime. Okay, if you have a problem and your neural network is not working well yet, there are like 2 ways you could try to improve. You could make the network smaller, so go towards left side of the variance bias trade-off, and thereby have less parameters, less flexibility. If you don't have much data, maybe you see that your performance increases a bit. Or you can go to the right-hand side and just throw more and more parameter at it and see what's happening. And one way to support this occurrence of the interpolation regime, at least what people tended to observe in practice, is, as I said before, SGD, weight decay. So shrinking the norm, or encouraging small norm solutions, weight dropout. So just look at those links. I'm not going to explain those things into detail in detail, but yeah, maybe you're starting to notice I'm somewhat torn between criticizing this whole thing as alchemy and at the same time having to acknowledge that it works really well and trying to share some of the tricks why it works and the intuitions that that people build up with these things. Okay, take it as a starting point if it piques your interest. All right, and on we go to an overview of methods and applications. Quick warning, this part is a quick overview. Don't worry if you don't follow some of the methods. If you find something very interesting, just follow the links and enjoy whatever you're finding on the way. There's also more references in the end. Also, everything I'm showing here is coming from my own set of interests, and it's not exhaustive. Okay, Confnets. I was really asked to cover these, and I think that makes sense because Confnets were at the origin of like the current big wave of neural networks that we've seen. And they do one really smart thing that we already discussed in the first part of the lecture, and that's inspired by the visual system. And what they do is basically, if you take an image, like this image of a car here, you could, of course, compute everything, like all the visual features, like extracting edges from it, or like extracting like local curves and the color of the sky, etc. You could learn all these little filters again and again for each position in the image, or you could learn them once and then just convolve them and shift them over the image and check at each location. Is there an edge? Is there a piece of sky? Is there a curve? And that's the idea behind Confnets. Again, with a blog post here. And we're basically learning filters and then we're stacking them. So let's unpack that a little bit. First, another motivation for why we should do this. If you think of an image, and this is another picture taken from the Statistical Learning book, like this image of a tiger, there are low-level features, like for instance this upward curve, and that's appearing at different positions, like here at the mouth, or here like at the bottom of the eyes, maybe, or the chin. And these low-level features can be combined in like a hierarchical way into high-level features, like here this upward curve is going into the eye, it's also going into the mouth. And then those high-level features, there's a mouth, there's an eye, there's ears, can be combined into something even higher, like the concept of a tiger, independent of whether the mouth was a little shifted in one image or the other, or maybe even occluded. And this hierarchical processing is something that we also saw in the first lecture happening in the brain. The retina is, I'm really oversimplifying now, but the retina is like extracting edges. Then primary visual cortex is looking at like oriented parts and maybe a little bit of textures. And then we're going up to higher areas like inferior temporal, where there's concepts of objects emerging. Like here, the concept of a cat. So hierarchical data processing is a good idea. The brain does it, and Confnets do it. And maybe that's one of the reasons why they were so successful. Okay. One thing you really have to do, I already said this in the first part, I'm going to say it again, because if you get into neural networks, this will be the first couple of weeks for you, is wrapping your head around tensors or feature maps and Confnets. So images are like 2 by 2D arrays of pixels. We also have color channels. So like a standard color image has 3 color channels. So we have this 3-dimensional block, pixel by channel. I think this so far is easy to understand, but then we keep on adding more and more dimensions, and we get these higher dimensional tensors. And much debugging in neural networks is actually just checking that the axes over which you're multiplying and adding stuff works out, at least in the beginning. At some point it clicks, and then it starts making fun. Okay, What is a convolution? So here's a few diagrams that I stole from Wikipedia. Just feel free to go through the article. The idea is that I think I hope you've seen this already in your study courses before. So if we have two one-dimensional signal, like here, this F signal and this G signal, convolution basically means, so if we're convolving F with G, that means we're taking F as is. So you're seeing this blue thing here, it's just F. We're taking G, we're swapping it around, or we're turning it around. And then we're multiplying it at each possible location with the value of F. So it's like shifting across F. And then we're getting this output curve, which at each point is like either the inner product of the two or the integral, depending on whether we're in discrete time or on continuous signals. Okay, so that's a very, very brief explanation of what a convolution is. Yeah, maybe surface this deep on this. All right. What is a convolution in 2D? Same thing. We're now just convolving over the field. So here we have an image. Let's look on the right at this nice visualization that I stole from a blog post. We have this image down here, this blue thing. And then we have a filter, this gray thing, moving across it. And we've also added these little fake pixels at the boundaries. This is called padding, so that we're able to move also on the borders. If we didn't do that, then the output would get smaller and smaller every time. And then the output of each location, so let's say the output at this location is basically these 3x3 pixels multiplied with the 3x3 filter weights and then summed up. Okay, I hope this is somewhat intuitive and makes sense. If not, check out the blog post. Okay, so now I'm just building this up slowly. We have to remember we're doing the same thing on a three-dimensional tensor with the color channels of an image. So now we're just moving this this cube around the image, and make sure that this matches the width of the cube or the depth of the cube. Okay. Convolutional pooling, another important feature in there. This is basically, so like max pool is taking the maximum pixel in each n by n window. So we take the first, let's say we do 3x3 max pooling. That means we look at the first window, we check what's the maximum pixel in there, and the value is 3. So 3 is what we get. We check, let's say this window down here, what's the maximum value in here? It's a 2, and we get a 2 down there. So this is, it's somewhat similar with convolution in the sense that you're like looking at each location, but instead of computing an inner product with the weights in your convolution filter, you're just taking the maximum of whatever is there in this window. Okay. And then the final layer, so the first couple of layers in a Confnet are convolutions and max pooling. But then we come to the last couple of layers. And usually what happens is in, like, let's say the penultimate layer of these convolutional layers, you're doing a max pooling over the whole image. And then what happens is before you had a three-dimensional tensor. So we had a block like this, like height, width, and depth. And then we're doing a max pooling over the whole image. That means we're squashing space down into a single dimension, and the output will then just be a simple vector. So we were in, oh no, we're not in R3. I'm sorry. The tensor was three-dimensional, and afterwards the tensor is one-dimensional. Okay. And sometimes if we don't do max pooling over the whole image, another thing we could do is just take the remaining pixels at each location and concatenate them after each other and make a long vector. And this is what's called flattening. So there's a flattening layer here in this drawing. And then afterwards, we just have a vector again, so we can do a matrix multiplication from the left. And this is what usually follows in the end. You just have a couple of matrix multiplications and value nonlinearities or whatever others you want. And we saw in the first part of the lecture that this is basically, again, the good old multi-layer perceptron. Okay, so this is basically a Confnet. Extremely successful, and you will definitely walk through using one of these if you're doing any of the tutorials. Maybe you've already done that. Okay, transformers. So I'm going to be a bit more brief here because I haven't really worked that much with transformers, but it wouldn't be fair to skip them because they are so ubiquitous these days. They are so if you look at the statistical learning chapter 10, there's one section on Confnets because they're important, and another one on recurrent neural networks. So if you have a time series, then you want a neural network which basically goes along the time series and like does some temporal processing there. This was all good in the past, but then a few years ago, people from Google proposed these transformers, which tended to work much better on temporal data. And I think you should look at the references if you want to see the speculations of people why this is the case. Anyways, what they do is they allow really long-range interactions for sequence data. So if you have a data point here and that interacts with something you saw earlier, and this is far apart for an RNN, a recurrent neural network, this is difficult. But for a transformer, often it's easier, or at least that's what people argue. And they're widely deployed in language and vision applications. There's really cool stuff happening with transformers. So you should be at least marginally aware of them. I think this is the original paper, Attention is All You Need, some people from Google. This is a pretty complicated looking drawing, so I'm not going to go through it. I think the blog post is actually this one down here. That's where I got the graphic from, and this is doing a good job in explaining it. But just for the quick overview, the idea behind a transformer is that you have a sequence of inputs, and then you're computing something that looks like an interaction between each pair of your inputs. So like, let's say we have this input chain here of 4 things, like 4 words in a sentence. We want to make sure that everything has the chance to interact. So we're basically computing like little interaction values between all 4 by 4. So we end up with this 4 by 4 matrix, which tells you, okay, this is how much the first one interacts with the second one. This is how much the third one relies on the fourth one, and so on. And by doing this, we can basically scale the different inputs or the different elements in the sequence according to how important the model thinks they are. People like to call this attention because you're basically highlighting different parts of the sequence that seem to be important. I thought this was a really cool illustration, the GIF that's running here below. But I read this blog post again just before giving this lecture, and I think I'll probably make the explanation very confusing if I try to do it now in 1 minute. So if you find this interesting, and there's a lot of reason to find it interesting, I mean, it looks again like someone just pulled out more linear algebra out of their head and threw it on the pile and started working better. There's certainly some truth in that. But all the cool things that you can do with transformers at least merit that you like give this 5 minutes and look at how they work. If you stay in neural networks, you probably use them at some point. All right. Transformers used in GPT-3, maybe you've heard about this in the media. It's a very influential but also controversial language model. Big controversies because this model started like reproducing a lot of bias and even racism that we had, and that it probably learned from the data sets. So there's a lot of discussion there. But it also sparked like a new wave of AGI, artificial general intelligence hype. So people always arguing that this is maybe the way towards building conscious robots. But transformers are also used in really cool language vision models, like here Clip and DALL-E, which I think are both from OpenAI. And just as a little taster, this model can take can combine language and vision cues. So like the text prompt that this model received is an illustration of a baby daikon radish in a tutu walking a dog, and then it makes these cool drawings, which actually look pretty decent. I was absolutely baffled when I saw this first time. It's very cool. But you can also use it to do useful things. Okay, that was my pitch for transformers. Now, so I've spoken about Confnets and transformers, two very important architectural things. But let's also think a bit more about the kind of modeling approaches we can take with deep learning. So far, we've always been speaking about regression or classification. You get some inputs, you predict some outputs. But what if instead of learning, so like in regression, we're always trying to estimate the conditional probability of our outputs given our inputs. But what if instead we want to find a good model, let's say Q of X, which somehow approximates the true distribution of X. So like, let's say X is the distribution of natural images. And here's just another visualization of ImageNet. So let's say this is the distribution of natural images in the world. Extremely complicated distribution in a high dimensional pixel space. Very, very difficult to model. And the purpose behind generative models, or deep generative models more specifically, is to find a good model of this distribution. Okay, so sometimes we don't just want to do prediction, but also inference, such as fitting our model to a complicated probability distribution, for instance, distribution of natural images. All right, there is a number of really cool deep generative models. So here are 4 of the different categories from a blog post down here. I am going to speak first about GANs, then about diffusion models, then about VAEs, and I'm going to skip flow-based models. Not because they're not important. Mathematically, they are very beautiful, and I'll add a reference on later where you can go and check them out for yourself. Okay, so first GANs. So this was a really a big splash when they came out. The idea is so cool, and it's very quick to explain. So you have a 2-player game. There are 2 players. One player is trying to produce, let's say we stick with natural images as the data distribution, just as our running example. One player is trying to produce something that looks like natural images. The second player takes it and says, okay, this is a real natural images, and that's just a fake from you. And they play against each other. So the faker, the forger, so I think one way of explaining this is like with art forgery. The forger has to try and come up with better and better fakes. And the discriminator has to tell which is fake and which is real. And so you're training them against each other. In the beginning, everything looks fake, everything is like really terrible. But over time, like the things that the generator is producing start looking better and better. And at some point, they become almost indistinguishable from real images. So it's a very basic idea. You have like these 2 playing a game, and while getting better at their game, we as modelers are getting the benefit of having something that produces realistic looking data. And not just natural images, all sorts of data, of complicated data distributions have been modeled with generative adversarial networks. Okay, just quickly, the way you do it is you sample a simple random noise vector, like let's say like from a multivariate normal distribution. You feed that into a neural network, And usually this is a Confnet producing like an image output. And you get a number of like different fake images. You also take a number of real images, you show them to the discriminator, and the discriminator has to say, are they real or are they fake? And then basically the generator is trained to fool the discriminator. And the discriminator is trained to get it right. So that's the setup. There's I'm not putting any formulas here. Go check them out. There's actually some really cool theory on generative adversarial networks. I promised in the first part of the lecture that if you feel like this whole thing is too much engineering and there's not enough mathematics and deep learning, check out some of the GAN theory. It's quite beautiful and quite involved. Okay, and just as an illustration, here are some images generated with GANs, and I think they look absolutely mind-blowing. Or at least they did a few years ago when everything before that just looked rubbish. Okay, basic idea behind GANs. I should also say that they are extremely fickle to train, and it's quite cumbersome if you embark on modeling your data with GANs. And you don't get an explicit model. You get something which is able to sample from this complicated distribution, but you can't, for instance, compute likelihoods. Okay. Deepgenerative diffusion models. So this is, again, something really cool. They're the current state of the art. So everyone always speaks about achieving state of the art in machine learning. They're the current SOTA image generation models. So they're the best at generating images. They're also they give you an explicit description for your distribution. So like you can compute the likelihoods of your data, for instance, which is much more appealing than just being able to sample from it. They have really cool roots in statistical physics, if that's your kind of thing. And some they're proper probabilistic models, so you actually get like an expression for the data probability. And again, there's loads of interesting theory in there coming from stochastic differential equations. The basic idea behind them is that you transform a complex distribution with a diffusion process over time into a simple one, like again, back to like multivariate normal. So the way we can think about this is we have a data sampled from this complicated spiral distribution in 2D. And now each data point is just diffusing over time. So you're seeing like everything spreading out. Think of heat equation. And at the end, you just have this maximum entropy Gaussian blob there. And this is something that we can model very easily. This just has like a mean and the variance in each direction and a covariance. This is a very simple distribution. We can measure probabilities here in this Gaussian, and yeah, Gaussians, we're happy. The cool thing about this is if you set up your differential equation, your stochastic differential equation to fulfill certain conditions, you can actually do the inverse thing and start with the sample from a Gaussian and then like diffuse it back in time and get back to this complicated distribution. So when I first saw this, this looked like magic, and there's actually some really cool theory behind it explaining why this works. Basically, you need to model the score function, so how your distribution is changing at each point in time. Okay, so that's the basic idea. You go from something complicated to something easy, and this works not just on simple 2D distributions. Let's go back to images. This also works on image distributions. So we have like the complicated, daunting distribution of natural images, and we just like add more and more noise to the pixels until we're basically in a white noise. So this is just like a broken TV. This is like a white noise sample of pixels. We have this forward stochastic differential equation, and we set it up properly so that we can also do the reverse. We sample like white noise trash, and we go back in time using the formulas we set up, and we actually get out an image again. And here is some of the math. You don't have to read it. probably makes more sense to read the paper if you really want to understand it. The cool thing is, through this process, you can compute how the probability density changes, and that way you get an expression for instance, likelihoods. So this is a really cool recent paper where people use it, and this is a shameless plug of my own work from last year, where we tried to use this in some application and hoped it would help, but it did not anyways. Okay, cool. So these are diffusion models. Next thing, variational autoencoders. I think I could probably give a whole lecture about VAEs because they're so exciting. And also, so I think they are probably the most used deep generative model that people are routinely resorting to in deep learning. Widely used, inspired by variational Bayesian inference, if that tells you something. If not, just Google it and look it up. The idea is that we have some complicated distribution. And instead of trying to model that complicated distribution, so let's say, again, like P of X, instead of modeling that, we just say, we take something simpler that we can manage, and that's our variational distribution. Maybe the additional bit you should know here is that the complicated distribution that we're trying to model here is not the original distribution, but we have a latent variable model. So we have X images, and then we have a latent variable, like a compact little description of images. So like maybe something that tells us what's in the image, at which position, which color, etc. And really what we want to do here is we want to know the distribution of the z's, and we approximate them with something simple. And again, that turns out to be a Gaussian. And then if we want to measure, for instance, likelihoods, of course, that's pretty simple. We can just marginalize out by saying, so this is the probability of X given Z times P of Z. And then you're integrating out the Z's, where Z is this latent variable thing. Okay, and so you have a generative model. You can measure likelihoods of your data. You have a latent variable, which is usually much smaller in dimensionality. So you have like compact description of your data, which is really cool. And the whole thing is differentiable. So like in here, we're doing something with probability distributions where we're taking samples in there, we're computing entropies and KL divergences, we're doing all this like fancy probabilistic analysis in the center part on the latents. But at the same time, it's set up in such a way, and I think this is really, really beautiful and smart about this whole idea, probably also why it became so extremely successful, is we do it in a way that doesn't break gradients. We can still back propagate through the whole thing and train our encoder, which gives us like this variational distribution as an approximation, and a decoder which generates data from this latent code. So this was very brief. You're most likely confused if you haven't read the paper, but I think this paper is always worth a read. Yeah, and then there's also a blog post here, maybe with a better description. Okay, variational autoencoders, deep generative models, and they give you like a latent code, which is really cool. Why is that really cool? Because we can do cool things with that latent code. For instance, disentanglement, another thing that's dear to my heart and I've been working on in the last few years. So VAEs give us a compact description of the data. For instance, think about this scenario. We have a very, very simple world. It's a visual world again, where each image has a description. So Z is our latents, and they tell us which shape, how large is the shape, how is it oriented, and what's its position in space. We send that through some data generating process. Maybe if you want to think about computer graphics, this is like your graphics engine. You give it some parameters and it renders images. And the images you get, so now we're in the axis, they look like this. So this is, by the way, the famous D-Sprites data set from Google DeepMind. And it's like different shapes in different positions with different orientations and different sizes. Okay, and now the question with this data set is, if we only have the X, we have only the images, can we learn a function which takes us from X back to the Z space? So now we have like some estimate of Z, such that the Z hat that we got are somehow equivalent in some sense to the original Z. This is called representation learning. This field is a bit more broad. If you look this up, there was also like a lot of work on this in recent years. Keywords to Google for are contrastive learning, where people use it on natural images. But the thing I want to focus on here is really the question, if we only have the images, can we learn a function f that takes us back to Z space such that we recover the original factors in the data? Can we do inverse rendering of images? That's also one way people thought about it, and get back the parameters of our rendering engine. A very cool problem, because like you're getting at the underlying sources, like the true factors behind what generated your data. And first of all, the bad news, or maybe to bring this into context, deep learning likes to invent things new. I'm going to come back to that in a second. The same setup has already existed for at least 3 decades. And we know it. Maybe you're familiar with independent component analysis. I think this was not covered in this lecture series. It's basically, it's similar like PCA, but you're trying to, so it's like a linear way of modeling your data, but you're trying to find something, the original sources in the world. Don't have time to go into it. Look at the Wikipedia article, or if you stay in data science, you'll know at some point what ICA is. As you can see from the title, nonlinear ICA is basically the same thing as what deep learning people called learning disentangled representations. Okay, so what's the setup? In independent component analysis, we're looking for some original sources of which we have mixed observations. The standard example here is you have a room. In this room, there are a couple of speakers, and they're each giving some weird monologue, like at a strange cocktail party. And you also have some microphones in the room, and every microphone gets like some mixture of the speakers, depending on how close it is to everyone. And so you have like, say, 4 speakers, 4 microphones, and then you have these recordings from the microphones, and there's this like overlaid babbling. And the question is, can we find the inverse of this mixing matrix, which gives us back the original sources? And in classical ICA, under some not too strict assumptions, we can prove that this is possible if this mixing function is linear. Now, if the sources are non-linearly mixed, so if you're not just like computing distances between microphones and you have like a matrix that describes this, if you have like some nonlinear function, for instance, a computer graphics rendering engine, you give the graphics engine some parameters, and that's a nonlinear function. Like if you take an image with an object here, an image with an object here, then if you add those 2 images, you have like both objects in there. You don't have an object over here, which would really be the additive of like the two position vectors. So like this is like a nonlinear mixing function of the sources. So if that is the case, then we can actually prove, and people did this in '99. Here's the references from Apo Havarinen and Pajunen, that finding the right solution is almost surely not going to work. So very, very cool result. Let's just go back 1 slide for a second. It means that if this process is nonlinear and that everything you get from your data are these, then it's basically impossible to find a function such that the z hat that you find are equivalent in some sense to the original sources. You're lost. There's no way of getting back those original sources if G is nonlinear. Okay. And you might have said, well, why have deep learning people been doing this for years if it's impossible, like which we knew since the 90s? That's maybe one of the criticisms to have with neural network research. And here is a critical recent paper, which was highly acknowledged, got a best paper award because it basically said, hey, we've known this for a while. This is impossible. Why are you doing this? However, and I wouldn't be telling you all of this just to bash deep learning if there weren't a positive outcome as well. The good news is that you can actually make this possible if you make further statistical assumptions. For instance, in the original proof, what the authors assumed was that your data is independent and identically distributed. You're just drawing, you're just flipping a coin all the time. And instead of having IID data, if you have, for instance, temporal sequences with dependencies between data samples, you can actually make this work. There's lots of great theory. I think these were like the first two papers showing that it could work. Then this is coming more from the, so these are nonlinear ICA papers. This is coming more from the machine learning world, actually the same authors as this paper. And then again, a shameless plug of my own work from last year, where we showed that the temporal dependencies you see in natural videos are enough. They give us enough statistical additional structure such that we can not only show that we can train models which do this correctly, but also prove a theorem which shows that we get back the correct solution under some not too strict assumptions which are matched to natural data. Okay, maybe that's also a good hinter, like these three papers and this one, if you want to do deep learning, but you don't want to give up all the cool math you've been working on. All right, this was it on deep generative models. We spoke about GANs, we spoke about VAEs, we spoke about diffusion models. We did not speak about flow-based models, not because I don't find them interesting. I think they're really interesting and very relevant. Here's a reference to look into them. The basic idea is you build a neural network which is invertible. And then you can use the change of variables formula to compute how probabilities are changing as you're going from a complicated distribution again to a simple distribution. So somewhat similar to diffusion models, but maybe more discretized. Okay. You're probably very overwhelmed by this already. As I said, it's quite a tour de force, and it's just to, these are just meant as appetizers. Follow the links. This is probably not going to be relevant for the exam. Most likely, I'm going to speak to Steffi that she doesn't test you on any of this because it's really just to give you a broad sample. Okay. Some more really cool things. Again, this just reflects my own interests that are happening in deep learning. Robustness. How can you train models on one domain, for instance, sunny images, and have them still work on other domains? We had this originally, the self-driving cars. Do they still work in the rain? There's a benchmark there. Shortcut learning. Neural networks, so this is like the standard example here. Neural networks learn to recognize a cow on green pasture, but they cannot recognize on the beach because they haven't learned the right concept. They just learned to see, oh, green background, yeah, cow. Yellow background and waves, no, probably not a cow. So they haven't really understood what a cow is. They just learned some shortcut for getting this right. And this happens all the time. So here's a reference on this. Adversarial robustness. So the first 2 points were about what if something changes about my image distribution. First, I have images from like sunny times or green pasture, and then I'm going to like rainy times or beaches. And I want my model to work well. Can it work if we change this in some way? The third point, adversarial robustness. What if we change our distribution in the worst possible way? So like what is like the what's the worst possible change of the distribution, such that a human looking at those changed images can still give you the right answer, but the model is completely off. This is a very, very tricky area to work on, because this worst case scenario means you have to try as hard as possible to beat your own model, and people don't like to do that. And that's why there's a lot of noise in this area. Anyway, it's also theoretically quite pleasing, and I think it's really revealing some of the key aspects of neural networks as well. Then deep generative models, we spoke about them. There's a recent workshop with more cool work, just click on the link. Unsupervised learning in general is a very broad area. How can we learn useful representations of images or other data types without any labels? So this is, I think generative modeling is a subset of unsupervised learning. And here's what I mentioned earlier, recent success contrastive learning, where people just train a model to learn something about natural images, and afterwards they do a little training on top, and suddenly they have a really good classifier. So it has like learned something about the structure of the data set, so to speak. Geometric deep learning, again, mathematically very, very challenging, pleasing if you want, where you're doing deep learning on manifolds or on graphs or anything other than the usual Euclidean vector spaces that people are using everywhere else. Then fairness, interpretability, and responsible AI. I mentioned earlier that GPT-3 had some controversies around it. So here's a blog, the story, and then the controversial paper that triggered a bit of a PR problem and quite some criticism in Google research. And the whole point here is that we're building these complicated models and we're just throwing our data sets at it. So like I think the latest GPT-3 is like trained on very broadly sampled text sources from the internet, and it's picking up on all the unfairness, the insults, the bias in the data. It's being racist, and the question is, or like maybe different example, if you build a model which has to predict if someone's going to default on their credit, and the first thing it picks up is their ethnicity or their gender or some other protected attribute like that. Of course, that's something that that we don't want to build our judgments on. So this is for fairness. Interpretability, if you have a scan of a lung and a radiologist says this is healthy and the model says no, this is early lung cancer, then you want the model to explain why and like tell us what are the reasoning steps, how do you come to this conclusion. Same with a self-driving car, like why did you not stop at this traffic sign? And yeah, so this is like a very broad area. It's dear to my heart, and I think everyone should have this on their minds. If you go into deep learning, this is extremely powerful. So many cool things you can do with it. So do make sure to also spend some time, if not your whole research career, on figuring out how to make these things fair, such that everyone profits from them, and also responsible and safe to use. Okay. Then deep reinforcement learning. If you've seen all the cool advances in recent year on like AlphaGo beating the human champion, or StarCraft, or poker, this is all deep reinforcement. So it's reinforcement learning is something from the 90s, and it's spiced up with neural networks, and you get deep reinforcement learning. So this is where much of the fame of DeepMind came from. These days they're doing much more than that, but yeah, also very, very cool, and also very very asked for if you go into industry. There are so many applications for deep reinforcement learning, where basically you're trying to do like a control problem, where you just click on the references. I won't do it justice now if I'm trying to explain it in 10 seconds. And then the last thing that I also find really interesting, and I think that wraps up this lecture series nicely, is I started out with this distinction between logical reasoning. So you remember rule-based, does it have a seat rest? Does it have legs? Then it is a chair. Versus implicit rules or neural networks. So like learning something from data without giving like a clear explanation for how you come to a decision. This distinction also comes up here. Like if you want it to be interpretable, like the logical thing, the logical reasoning system is interpretable. You just have the rules, you tell them what rules you applied. The implicit one is not, and that's one of the challenges there. And in the more general setup, people are trying to combine these two things. How can you build a model that reasons like humans do and that can explain their reasoning, but which is robust to all these little noise variations and continuous signals in the real world? So I think this is really, really exciting stuff happening here. Funnily, the same debate existed previously. If you look back to like the late 80s, 90s, there was a long scientific discussion between symbolism, so that's using logical reasoning, versus connectionism. And it's the same debate. So everything is coming up again. Also, people do hope that if you somehow get an integration of these two things, you might also be able to do better on these things. So just as an example, the cow, once you've learned the concept of a cow and not just like the statistical regularities between cows and the green meadows behind them, once you've learned the concept, the symbol of a cow, you should be able to find that symbol again, even in an unusual context. So there's some, so if you get this, if you figure this out, you have important things to say on fairness. You have important things to say on all of these first 3 points. By the way, I should have said these first 3 points are all about out of distribution robustness. Maybe just look this up on Google. OOD generalization. So in distribution, you're testing your model on the same distribution, out of distribution, OOD. Okay, I didn't slow down. This probably made it even more confusing. I hope I, again, gave you some good pointers to further spark your interest in this exciting field. And now on to some closing remarks on if you do want to work on this. Maybe here are some quick pieces of advice. I couldn't find the origin of the source. If you find it, please email it to me. I'm sure someone said this and I just couldn't find it when I was preparing the lecture. The quote goes as follows: mathematicians try to unite different ideas under the same name. Machine learning researchers try to reinvent the same thing over and over again under new names. There's a lot of beauty in mathematics because you're trying to unite concepts, you're seeing the similarities. There is also a more organic beauty in machine learning in the way that like different things come up, they evolve. Sometimes they are similar, sometimes they are different with like little changes. This is, I don't know, this double-edged sword. Like you come up with this great diversity of cool things happening. And there's a lot of progress. At the same time, if you're in this for a while, you hope for some like unification and like, okay, these 3 papers are really just doing the same thing. And so are these 3. And why are you reinventing the wheel all the time? Okay, this being said, the field is full of hype. It's already pretty full. At least the big tech companies start saturating, and it's definitely becoming more difficult to join them as machine learning researchers. Some miscellaneous pieces of advice: if you write a paper, you develop a new method, pick a funny name. People do that all the time. Sell your paper well. People are really blowing up their papers, and I should say at this point, but don't sell out, don't oversell. do proper science. If you write a paper about that one lucky seed, and this actually happens, I'm not looking at reinforcement learning work, where people beat the current state of the art by 0.1% performance, like totally insignificant, different seed, sucks, and then they write a paper about it. Don't be that researcher, like have some scientific standards. Some parts of deep learning, and I really hope I, if not convinced you, at least gave you some motivation where to look further. Some parts of deep learning are very theoretical and mathy if you prefer proving theorems. And then, of course, have fun. Or maybe I should finish with do the right thing. Don't use deep learning just to suppress minorities or reinforce biases. I don't know. Be a productive part of this community, and let's try to make our world better with the cool possibilities of deep learning. All right. Here are some additional resources. Papers with code. The main website, I'd say, for looking at different data sets, at different models, checking which model is best on which data set. Also seeing, there's also links to GitHub repos with like standard implementations of papers. This is a great resource. Machine Learning Street Talk, very influential podcast on deep learning, great fun to listen to. So here, there was some discussion about the interpolation ideas that I mentioned earlier. If you look at recent podcasts recorded with Jan LeCun, there was a long podcast on like sparsity in high dimensional spaces, quite interesting. And then really great blog posts. You already saw them, the links throughout towards data science and Medium. They have really great blog posts on deep learning. And then if you stay in this field, most important conferences to keep on your radar: NeurIPS, ICLR, ICML, AAAI, CVPR, and others that I can think of right now. Okay, and then that's my last slide. So thanks very much for watching this video until now, and enjoy the exercises. Thanks for attending this course, and I hope you have as much fun and exciting research experiences as I had with neural networks. So long.